right, good morning. We're Team Intruder. My name's Candace Ross.
My name is Nadia Green.
Joyce Sintel.
I'm John Delapetta.
I'm Janetta Bratcher.
As Dr. mentioned, we'll talk about hardware Trojan detection, prevention, and medical systems. So these are our 5 key points we'll go over today. We'll start off with just a brief overview of our project, then a user case. You can kind of get a real-life scenario of our project. We'll go through how we designed our project, how we implemented it and tested it, and then finally a wrap-up.
All right, so we all have computers, right? And we all have antivirus software. We want to make sure our computers are safe and secure. Well, the thing is that most hospitals' databases use computers as well. Most databases are computers. So our project just goes more in depth of the computers that are used in hospitals and how they're being secured. And we actually come up with integrating some security primitives into the systems that are used in hospitals. So this is a magazine from IEEE 2015, which is saying that computing in healthcare is relevant. It's today. It's now. So we kind of use this as background to get a little more in depth of our project and where we can go with this. All right. So what do we want to do? We want to take a system and figure out how can we secure it? How can we develop something so that hardware Trojans or malicious software can't get into it?
So what is a hardware Trojan, you might ask?
Aha. So a hardware Trojan is a piece of software. It could be a program. It could be a piece of code that can get inside a circuit and maliciously change the circuit, either to reap information or to make the circuit do something that it's not supposed to do, etc. All right, so in going further with our project, we wanted to make sure that there are a few things that we touched on and kind of formed our project off of. We want to make sure that it's size efficient because it's in the hospital, possibly it could be in a patient's room, and we don't want this huge computer sitting in the room with them, taking up power and heat and stuff. We want it to be fast. We want it to be able to do things in real time. So it doesn't take 6 years to up the command or change a dosage. Also user friendly, because we have to realize most doctors have so many things on their brains. They don't think about, okay, I have to, enter a password, I have to enter this, and I have to do this to make sure that the computer works the way it wants, the way they want it to work. So it has to be user friendly. And then lastly, all of these things with security primitives. We want to make sure our information is confidential so that no one else knows it except for the doctor. We also want to make sure that it has integrity. Nothing can be changed. Nothing can change it, or it can be read from without authorized permission. Yes. So how are we going to do this? Well, we came up with a solution. And we could do a two-pronged solution, 2 parts to it. The first part is, let's authenticate. Let's make sure whoever's trying to access this information is the person that we want it to be. So, example, it can be a doctor with a doctor ID number. It can be a hospital authority with an ID number. So that's the authentication part. And with the authentication, we set it up so that it sends a yes bit or no bit to the FPGA, that's where we get the command. So maybe we want to up the dosage. We'll take the command through the IR receiver. It's a remote, but it won't take the command until the authorization is bit, and then it'll take it and decrypt it. I'm sorry. So it comes in encrypted, and then we decrypt it, and all together we have our command sent to the medical device. So why is this relevant? Like I said earlier, most hospitals use computers for their databases. These databases are called personal health records. These health records have information like date of birth, your social security number, possible medical history that you have. So like high blood pressure, it can be your weight, very sensitive information that isn't necessarily given out to the public. There's two types of personal health records. One type is tethered. The tethered PHR is organization-based, so it's based on the hospital. Hospitals provide applications, the interface, that will then, the patient comes and sees their information given to them, but it's hosted by that hospital or that organization. For example, Kaiser Permanente. The other type is untethered. Untethered is cloud-based. It's in the internet. It's controllable and it's accessible outside of the hospital. The patient controls that data, and the patient controls what data they give to the hospital. And that's the big importance of why we want to try to secure these systems.
All right, so this is a user case. So let's consider a setting, a busy hospital setting where both doctors and patients can both access the unsecured system. How do we know someone's not going to maliciously alter the system? So we assume that there's no protective security measures against the system. Both doctors and patients can both access the system. And lastly, it's a medical device controlled just by the computer. And then right here is a final schematic where the laptop and the Intel Galileo board are connected via USB. The FPGA and the Galileo are connected by wires. And we send the command maliciously by the IR, which is called the infrared transmitter, to lower the, to alter the medicine dosage pump.
Here's our three major design changes that we have for the project. We're going to talk about physical transmitter, means of communication, and cryptographic algorithms. For physical transmitter, we want to send, we're going to use a remote, any kind, to send to our board. So we're talking, in comparing to all of these cases, we're going to talk about in time, cost, resource, and longevity. Since we're using a D2I board, it already has a remote, so everything is already implemented. So for make our case easier, we use a remote. However, in future cases, we would like to discuss how we can use cell phones to send data to the system and in order to send command. And means of communication, we've been discussing about Bluetooth versus infrared. For Bluetooth, everything's already used in cell phones, devices, you name it. However, since in our D2I board, infrared is already implemented, so while we might discuss the use of Bluetooth in future works, we've been, there's already resources, such as we already have a manual for the D2I board, which we look at in order to communicate the IR receiver and the remote. So in this case, we choose infrared in this case. And now the biggest decision that we had to make in this semester is that for cryptographic algorithms, that is the system to help us to make prevention, make it more secure. However, we talk about RSA, RC4. It's pretty much public key versus private key. RSA is public and RC4 is private. However, earlier in the semester, we already implemented RC4 to our system. It's very more time efficient, means that we already implement the board to our programs within at least 10 minutes. So compared to RC4 is like, RSA, it's already about like 25 minutes implemented to get the kinks working debugging. However, the main issue is related to the keys. So since RSA uses two keys, a public and a private, it will make my system more efficient than RSA4. So, and also there are a lot of resources for RSA which we look up online for our resources. So we make that choice for RSA. And the callback 204, our final schematic, is that we're going to use a two-prong system for a laptop and the remote. So the remote will communicate with our board, and then the FPGA and our board will communicate with duplex communication with our Intel Galileo, and that will send our final command to a simulated device that will up the dosage, any means for medical procedure. I forgot to mention that the laptop said we use interface to input the data for the patients in order for it to be secure.
So how do we implement, test, and evaluate all of these different system components? Mainly we use 3 softwares: Quartus, Xilinx, and Arduino. So our first system components were the transmitter and the receiver. So we wanted to, if you recall, the receiver is located on the board. So we want to use the remote to send a command to the receiver. And then we wanted to make sure that if we press, for instance, a 3 on the remote, we can verify on the board that we're receiving a 3. Then we came to the algorithm, which is receiving our command. So we wanted to adjust our source code to fit the scope of our project, get rid of unnecessary inputs or outputs, and create new ones that we needed. Simulated this algorithm in Xilinx, and then we passed different registers or outputs to LEDs to verify that we were seeing our decrypted command. Then we connected the 2 modules together in Quartus. We passed the command from the remote to the receiver into the algorithm, and it was decrypted, and we wanted to make sure that that was happening. So we have a video. So we press 3 buttons on the remote, and we're decrypting. These LEDs down here will actually show the binary of whatever button you press. So here, the first button we pressed was a 1. Our decrypted command comes up on the 7-segment display, and then here, these last 4 LEDs, we got a 0, 0, 0, and then our 1. So that's how we know we press the 1 button. We press the 4, so we're seeing,
Seven.
that's the 7. 4. So it jumps straight to the 7, so we have a 0, 1, 1, 1, and that's our decrypted command for 7. So different button, new command. Then we have our database, which we used Arduino to code this database. And we just want to make sure that if you put in the patient's name and the patient is in your database, you get a yes. If the patient's not in your database or you spell the patient's name incorrectly, it's not going to let you send any information. So the Galileo connects our pump and our FPGA together, and they communicate via GPIO pins, general purpose input-output pins. And we connected all of these things together in Quartus. And then our dosing pump, our simulated medical device, we're controlling via those pins through the Galileo, and we want to make sure that when all is said and done, we've authenticated the information and we've decrypted our command successfully, that the pump is turning on and it's doing everything that we asked for it to do. So here we just have a demo of how everything's working together. It might be difficult to see the patient information, but please believe that it is accurate. So we have the doctor input the information. We go to the board, we have this green LED on, which means that we authenticated. That was our way of making sure that we authenticated the patient. We sent a 1 to the board, and we saw our decrypted command come up. And then a light will come on over here. Well, it keeps. And then if we listen very hard, we can hear the pump has been turned on and it's working. So we're gonna find the demo.
So let's move into the resources and like a nice wrap up. So as was mentioned, we had 2 pieces of hardware that we used primarily. It was the DE2I board and the Intel board. Then these 3 pieces of software, Quartus and Xilinx, were used to program the DE2I board. We used our Arduino software to program the Intel board. Then the dosing pump, which we were graciously loaned by a fellow student, and a power supply to power the pump. So, how much did everything cost for us? It was free. We had no out-of-pocket cost. We got really lucky. The boards we got from Dr. Kim, and then obviously the fellow student, and the software was all free. So we had 3 primary conclusions that we drew. The first one, as Netta mentioned, our goal was to really secure communications, and we felt that was something we accomplished. So we had, again, the 2-prong detection system where we authenticated on the Intel Galileo board, and then on the D2I board where we did the decryption of the commands. The other big goal was prevention. Again, as Justin mentioned, if you're in a hospital setting and it's busy and it's not very secure, you want to make sure people can't just come and send malicious commands. So then that came through our Intel and our Galileo board. And then finally, with the personal health record system, again, we mentioned this is something that's becoming really prevalent. A lot of people are really looking toward using these PHRs. So we were like, let's really make our goal to secure it. And we secured the tethered method. That was because we had everything stored on the board. We did not use the internet. So we know the big part of the senior design projects are these vertically integrated projects where we really want to bring in underclassmen and grad students. So we think our project has a lot of room for growth and for continuity. So the first thing we talked about, we wanted to prevent and detect hardware Trojans. We spent a big focus on the prevention side. Moving forward, it'd be great to see some detection. Also, we used the infrared remote that came with our board to send our commands. Moving forward, you could either use a smartphone, because anyone here who has a Samsung probably has an IR transmitter on their phone, or perhaps Bluetooth, because again, that's something that's very prevalent. Medical device compatibility would be nice. We simulated our device, which you saw in the video and you also see in our demonstration. It'd be nice to have a real device. We ran into a few issues with that because it's all controlled by the FDA because it's drugs. So that was one thing that we had a bit of trouble with getting a real board. And then finally, internet connectivity. As we mentioned, we used a tethered system where everything was stored on our device. It'd be great to bring in the internet and see the untethered system as well. So that was our project. Do we have any questions?